Button here. So ta-da! Now, welcome to the new year. Welcome 2021. And I think I'm recording. Let's see, make sure. Yep, we're good. Okay, so Google Sheets or Google Docs here, we have the calendar for the rest of the year. Not that it's filled in, just have the calendar there. So we're looking at January going through chapter 4. We started it a little bit before, so let's see. Let's quick review here. This was basic graphs, weren't we? Do you guys remember a long time ago?
No.
Where I made you guys go row by row just to make sure you're participating.
Right.
And we made a table for Sine.
Oh!
There you go. The Grant remembers. All right. And then we had something look like this as well. Ooh, there's our sine curve. And so super cool. Few things that are super cool. First is along the x-axis, we have actually real numbers, right? Because that's what radian measurement is all about. The fact that we don't have 30 degrees or something else like that. So you can't have time in degrees. That's not going to happen. So if you have a pendulum that's going up and down, or a spring that's going up and down, you're not going to test it by degree measurements. We're good. And so we had to have some kind of radian measurement, some kind of real measurement along the x-axis. That's why we invented radian measurement. And then the y-axis is real numbers as well. All right, real quick here. Da, 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 da. I think we have this right here, just to show you where this is all coming from. Whoa, not supposed to do that. Something happened.
Right, Matthias. Good job.
I'm going to leave that page. Let's get back to the page. Hopefully reset itself.
Yes. I was wrong.
Yay, all right.
In my opinion, that is
A height base.
You are wrong.
Okay, I guess I was supposed to just move this right here. So, quick visual illustration, right? So the height is going to be what is marked right over here. And so you have the unit circle. We've been going circularly, and now we're going to go flat out this way. Okay, does that make sense to you guys here? So the x-axis now is technically the measurement, right? The angle measurement. So many lines. It's all confusing. Stop the lines. Okay, so with that done, we did the same thing for cosine. And then we also did this right here. We categorized a few things here for sine real quick here. So domain, there's never breaks in the graph, right? We can graph the sine curve no matter what. Range, the highest it's going to go is 1. The lowest going to go is -1. And then we have something called amplitude. First time. Amplitude just means how far are you from the middle to the top. So in this case, it was just 1. Let's go back to our little graph real quickly here. It's the middle point here, and then how much it reaches up. Or you could just say, look, it's going to be the range here divided by 2. Okay, we're good there. Getting there. Oh, back to here. Okay, period is how long it takes to finally start to repeat itself. We're good? So going back over here. So if you go up, then you come all the way down, then you get to 0. Then after this right here, you're going to start repeating itself, which makes sense, right? Once you go past 360 or 2 pi, you're going to start repeating itself. Okay. Clicking on the wrong one here. There it is. Okay. And the zeros. Zeros, according to sine, is just the every pi. And so it's pi right here. 2 pi, next 0 is going to be at 3 pi, I assume, is that right? Then 4 pi, then also negatively. So if you go 0 here, you're going to hit a 0 at negative pi, true? You're going to hit a 0 near -2 pi, -3 pi, and all that good stuff here. So not going to list them. You're just going to say it's k pi and k is an integer. So that takes care of all of them forever and ever. Okay, and even and odd. I think we covered this last time here. That's an even function. Even function has a reflection about the y-axis. An odd function has a reflection about the origin. So it's kind of like you take the reflection about the x-axis and the y-axis at the same time. It's kind of nifty that it doesn't work all the time that way. It's not like if you have a y-axis symmetry and x-axis symmetry, you have the origin. Good? So it's a little different. Okay, are we good? We caught up from last year almost? No.
I don't really understand.
Talk to me.
I don't.
At all, okay.
That's
Not a single thing.
I don't understand how this, so you go from the unicircle to the squiggly line.
Uh-huh.
I don't understand how that happens.
Gotcha. Going back over here. Let's see. Think about it here, guys. Sorry, slowly. Guys, real quick, talk with me some more, guys. And raise your hand if you're having the same difficulty. It's so weird. Go from a circular object to this. Are we good? No. Okay. Let's go concrete then. So let's say you have a tire or a wheel. We good? And you are trying to do this here. That's essentially what you're doing. Let me just jump to this. Oh, no. I'm gonna that way, do that way. Okay. I'm gonna draw my fake car. That's about as good as I can draw a car. And I have a wheel here and a wheel here. Are we good? And we are just gonna measure. So we're gonna arbitrarily draw this little line through the wheel like this right here. And we just need to measure the height if we have a little dot right over here. Little dot. We can even say where the air hose goes in. Does that make sense to you guys? Air hose goes into this little spot right here. And we're gonna measure the height of this dot compared to the center of the wheel. Does that make sense? And as this car goes backwards, we're gonna go backwards. Why are we going backwards? Just for the fun of it. So we measure this little dot here. And so what we do is we make a little graph and a little chart. That's what we're doing here. And so as this car goes backwards, let's say what? Let's say 2 feet, for instance, right? Then this little height is about right here. Then it goes back another 2 feet. Then its height is like here. Then it goes back another 2 feet. I'm exaggerating. So this is 4, this is 6, and as it goes back 6 feet, it's like that. Notice it's not a line, right? Because that little dot is curving up, right? So that last little piece here, right, as it gets to that little top, it's not going as fast as right when you started it, and it's going up. Good. So then it gets past the halfway point. Then at 8, it's going down, and the question is this going to be symmetric? What do you guys say?
Yes.
Absolutely, it's going to be symmetric, right? As it goes up, as long as it's steady, right? The dot's going to come down. And then at 12 seconds, or 12 feet, sorry, it's going to be the same exact level as the middle of the wheel. Are we good there, Matthias? Does that make sense? Sweet. Okay, so we're really going from a, not so much a type of graph, a situation, and then we're just graphing or modeling that situation. Okay, and for cosine, the only change is the dot starts on top. And we're going forward with the car this time. That's cool. I like that. On the spot. Okay. With that, let me just jump to this real quickly here. We did the same with cosine, is that right? So quickly remind ourselves what we did. There it is. There's cosine. Made you guys go through it all over again, right? As a class, you guys remember that one. Okay, so cosine, it starts on top, it goes down by the time it hits the halfway point, and then it starts going back up. You talk to me here. What is the period for cosine?
2 pi.
2 pi. Notice from the time it goes on top to the time it goes on top again, 2 pi. Are we good? And I get to bug people. I love bugging people here. So we're going to start from the right to left here. And tell me if you want to skip, that's fine too. Good. So Hayden, what's the domain for cosine?
Is it all real numbers?
Yeah, perfect. All real numbers. The only time you'd have issues with domain is if you have something like this, a squared function. Notice there's no graph on the left-hand side, right? The other time you have domain issues is when you have something that looks like this and you have vertical asymptotes coming down. You guys seen those graphs in Algebra 1 or Algebra 2? So those are the only two times you have domain issues. If you have a graph that's just kind of slowly, you can draw it without putting your pencil down or lifting your pencil. Perfect. Range, Amaya.
-1 to 1.
Perfect, yes. Same as sine. Haley, amplitude is 1. From the middle section to the top is 1 unit here. Cool. Rylan, even or odd?
Even.
Perfect, yeah, because it's symmetric about the x-axis or y-axis right here. This dot would go here, this dot would go here. We graph it again. We're good there. So again, just totally branching out at a whole new math branch of trigonometry, just because we make a little graph. Tangent. Let's go tangent. So we do the same thing with the tangent. And then the graph looks like this. I think that's where we stop right after we graph tangent. Cool. So I guess we better find out just real quickly here. So I need domain. I'll do R for range, P for period. Let me go back to this one. Oh, amplitude, zeros, A and P for amplitude. I'll go with zeros and even or odd. We'll figure out what that is. Okay, cool. Now we have a little problem because notice we have those little slash lines, right? Called vertical asymptotes. The graph is not going to hit those lines at all. So we have a vertical asymptote at pi over 2, another one at 3 pi over 2. So how about this? All real numbers. Except x is equal to, and how about this if I put k pi divided by 2, and you guys talk to me.
Can you explain what that means?
Sure. That little k value right over here, it's a nifty little way to only get little pieces of or spot pieces along the x-axis. So if you say k is an integer, let's say, you don't have a whole graph for k. K then just becomes just the 1, just the 2, just the 3, just the 4. Does that make sense, Grace? So if you want individual little pieces that you want out of a graph, you just use that. And you can define k however you want. K could be an integer, it could be an even integer, it could be an odd integer, could be a fraction divisible by 2. I don't know, you can do whatever you want.
Basically, that's just like saying that's the placeholder for where it's pi over 2 and then.
3 pi over 2.
Okay, so you're saying each time it goes, it's k pi over 2 in those spots.
But now we have to define k. So if I say k is an integer, I don't think that's going to work this time, because notice if k is 0, it hits 0. If k is 1, yes, it works for 1. If k is 2, we hit this one. That's not vertical asymptote. That's actually a 0 there. So it looks like I have, if you guys see it here, this is 1 pi, that's 3 pi. What's the next one going to be? That's a vertical asymptote. Is that 1 pi over 2? Then you have 3 pi over 2. 5 pi over 2 is perfect. Yeah. Next one, 7 pi over 2. Are we good? So how about if we do this here, where k is an odd integer. Are we good? Well, that kind of just ponder that, see if it makes sense. If k is an odd integer, then we have that 1 that we want, we have the 3 that we want, we have the 5 that we want, and it goes on forever. Love it. Love creating stuff. Because you guys technically are creating stuff in math right now, right? Because you're trying to figure out what would fit. That's cool. Range. How low does tangent go? How high does tangent go? Well, that's pretty low right over here, huh? Oh, yeah, that's a little different. So you can write it like that. You could also write all real numbers as well, whichever way you like. All right, let's talk about period. Period for tangent. So how long until it starts doing the same exact thing again? We can even look at starting at 0, right? Here's my 0 right here. I go way, way up. I have my break. Start very, very low. And I go to 0 again. After this spot, question, is it started repeating itself? Right here. Sure does here, absolutely here. But how about pi? Notice real quick here, this is 0 to 0. This is this one. Notice, let me just cut it real good. Can I just cut this? Pretend this is a cut along this little piece right here. So this little area here, is it the same thing as that area there? Yeah, starts off at 0, 0, right? It heads off to infinity, right? We get the cut, starts off low and gets up back up to 0. And so the period for tangent will be pi. Just takes those two values for it too. Okay, amplitude. From the middle to the top, well, it goes off to infinity. Forget it. There is no amplitude for tangent. In fact, only sine and cosine have amplitude. Good, because that's the only ones that actually go up and then comes back down. So how about none applicable? Anybody do those on applications here? NA? Zeros, oh, how fun is that now? Okay, zeros are at 0, are at pi, are at 2 pi, and you keep on going from there. So what do we have there? So 3 pi, 4 pi, 5 pi.
Would it be x equals k pi?
I think that's pretty close here. Just have to define what k is, right? Is k an integer? Is it an even integer? Is it an odd integer? Because those three usually are the differences. Yeah, so notice it's 0 pi technically, right? Then we have 1 pi, then we have 2 pi, 3 pi, 4 pi. That sounds like an integer to me, right? Is an integer. Okay, even or odd? Does it look like it does not look like it's symmetric along the y-axis. Is it symmetric about the origin? I think so. Notice this little piece right here. It's going to be, if you take this little dot here, it seems like it's going to be right here each time. Take this dot here, as you move it across, you'll be right there. Good there. So it is an odd function, just like sine. Okay. We could do this for the rest of them, but you notice how long it took us just to do, yeah, okay. Too much. Okay, so let me give you guys the other ones here. And as we start graphing these, we'll see actually how to graph them. But they're sine, cosine, and tangent. First of all, sine and cosine are the most important because we model a whole bunch of stuff with those, right? Tangent comes in It's a good amount of time, right? Then the other three don't come in at all. We don't, I mean, not at all. Very, very rarely will we actually model something with secant, cosecant, or cotangent. So, well, maybe cotangent the most. All right, let's jam with it. So here it is. Here's your 6 different graphs. Now notice in your front of your textbook, let's do that here. Front cover of your textbook or the back cover? Let's see. No, very big back cover of your textbook. No, sorry, it is the front cover. There it is. So you guys have all these guys with you already here. It's on the second column. So there's your sine, there's your cosine. We have tangent, cotangent, secant, cosecant. So if you need to refer back to it, go for it. Nothing just to point out, hey, look at that, domain, range, amplitude, period, and zeros. It's all there. How fun is that? And now, let's see if any one of those are slightly different. Let's talk about the differences. Okay, so let me do one more thing. Let me do one more thing with tangent. Since tangent has these little asymptotes, and so ASY, MPTO, ES, asymptotes. TO, glad I'm not an English teacher here. Okay, there it is, asymptotes. How fun is that for spelling? Sorry, flashback to holiday season, an elf. That's right, remember it says Francisco. Ooh, what a wonderful name, Francisco. Like asymptotes, what a wonderful name, asymptotes. Okay, sorry, holiday season still. Okay, asymptotes are fun. Now we have to figure out this one right here. That guy, that guy. And notice it's the same thing as the domain, is that right? So I want to show you a little something here. So I'm trying to hit the asymptotes exactly right, and we have the same exact pieces that we had here. It's just k pi divided by 2, right? How about if I do it a different way and see if this makes sense? You guys tell me if this is true. I'm going to define it as this. All the asymptotes are x is equal to pi over 2 plus k pi. You tell me if that is true. Is that saying the same thing as, oh, I have to define it, right? So k is an integer. I'm running out of space here. Okay, talk to me. I need to know this here. K is an integer. That piece right there, is that the same thing as saying this right here? So I think so too. Let's see, if k is equal to 0, that means we have our little pi over 2. Are we agreed there? K is equal to 0, it's pi over 2 plus k pi. Okay, if k is equal to 1, then we have ourselves pi over 2 plus pi, which technically is just 2 pi over pi. And did we just get 3 pi over 2? I think so. So maybe write this down in a note somewhere here. So pi over 2 plus k pi. And then underneath it, just put k is an integer, is the same thing as saying k pi divided by 2. And underneath it, just write k is an odd integer. Oh, good. So two different. This is k is an integer. Sorry, pi over 2 plus k pi. This one is k pi divided by 2. And then we just define k a little bit differently. So k is an odd integer. And that's still okay to do. Lots of graphing. Sorry, guys, let me get out of your way. So notice that whenever you define something, it's not really unique, right? You can't just say it one time. You can actually say it multiple different ways. You can still hit the same thing. So when you guys will be doing this and you make your own exception and you look back at the book and it's different, it still may be the same. We're good? It still may be true. You still may have got the right answer. It's just not the way the book is saying it. Okay, boom, boom, boom. I think we're good there. We looked at the other ones as well. Time. All right, few things here just to add to our little collection. So remember how we said that these guys are odd and even integers? Let's talk about it just a little bit longer. Oh, I don't want that. I want something like this. All right, there it is. And this is front cover of your textbook here. So front cover of your textbook, you should have all that information for each one of those. The three important ones are on top. That's the ones we use most often. Very, very rarely, sometimes maybe we use the bottom three, but the top three should be the ones. That's why we graphed them. Okay, so let's talk about this here. Let's grab the fact that sine is odd. Cosine is even. And tangent is odd. We just figured that out from the graph itself, right? We figured out the way the graph looks like. Sine and tangent, they have reflection about the origin. Cosine has reflection about the y-axis. But what does it mean that those are true? So let's do each one of these here. Let's go back to the unit circle, just real quick here, because if it works on the graph, it should also work on the unit circle. So for sine to be an odd integer or odd function, if I have the unit circle here like this, and I'm going to put right here, I'm going to put x comma y. Which is the same thing as, what is x? If this is 1 here, isn't x cosine, is that right? Cosine theta, sine theta. Everybody remember those? Are we good with those? Cool. And if we go down this way, so this guy would be positive theta, this guy would be negative theta. Agreed there? If that's the case, this is just an illustration for it. Tell me true or false here. This is x negative y, is that right? And then the value to it is cosine of negative theta and sine of negative theta. Are we good there? Okay, yeah, we have just enough time. Okay, so let's do this here. Let's prove that sine is an odd. We saw it from the graph, right? But in mathematics, we say when we see something in the graph, that does not prove it. We're good? Prove it means you have to have an equal sign that starts here and an equal sign that ends over there. And you're saying, oh yeah, now that's proof. So let's start off this. The proof that sine is an odd function here, we're going to say this: sine of negative theta equals And tell me if you guys agree, equals negative y, is that right? But the y value, the value even in by itself, right? Isn't the y value just sine theta? With a little negative sticking out in front? So in this case, this is the negative that comes from here. And the y value is this one right over here. Because the y value is still the y value. Boom, okay, so now we know what this means too. So whenever you have a negative angle, what we can do is we could just put a negative outside of sine and we can use the positive angle. So an example real quickly here. So sine of negative 30 degrees. In fact, if you have a calculator, just punch in sine of negative 30 degrees. Good there? What'd you guys get? Negative 0.5 maybe?
Yeah.
Cool, okay. And then isn't this also gonna produce the same exact thing? Negative sine 30, oh, just a positive 30 degrees this time. So negative on the outside, but we leave the sine value the same.
Same thing.
Same thing, okay, cool. And so what does this really mean? If we have a negative angle inside sine, what we can do is we can put a negative value outside of sine and we can use the positive angle. We can find the same exact thing. Okay, let's use the same illustration. Let's prove the fact that cosine is an even function. So I'm gonna go vertical. So everybody agreed there? Cosine of a negative theta is equal to, according to our chart, it's equal to what?
X.
Just the x coordinate, right? And notice the x coordinate here is exactly the same thing as the x coordinate there. So then that means that this is just cosine of theta. Ooh. Okay, so cosine being a even function just means this as an example here. So cosine of negative 30 degrees. And let's punch that in our calculator just real quickly here. And punch in cosine of positive 30 degrees. Let's see if they're the same value.
I did guess the same thing.
Yeah.
Oh, no, I didn't. One of them was positive, the other was negative.
That is so interesting. Positive though. I mean, did you stick a negative in front of cosine?
Yes, I probably did it wrong.
It's okay. So cosine of negative 30 and then cosine of positive 30. It gives you the same exact value. That's cool. We'll figure out why that's useful in just a bit here. Okay, can we prove this guy? So I'll let you guys think about it here. Go for it. This is one of those, hey, let me think what the definition of tangent is. Let me think about how I prove it. And we somehow have to have a negative on the outside, right? Because we're trying to prove that tangent is an odd function. Right, anybody think they got it? I could start singing Jeopardy. Do, 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 do. All right. Anybody with a preposition of possibly this is the proof? Or no? Let me try it. Let's see if you guys got the same thing here, since some people are shy to say it. So I have a tangent of negative theta. By definition, isn't it ratio of y over x? Is that right? So don't we have something that looks like this? Negative y over x? Because we're looking at this form right here. And if that's the case, that little negative could actually go out in front, just as a y over x, and that becomes, hey, isn't the ratio of tangent just y over x? So that just becomes negative tangent of positive theta, because now we're looking at this little point there. Okay, that's one way to prove it. Just another way to prove it is, instead of going all the way back to the x and y's, don't we have an understanding that tangent is actually sine over cosine? So can I do this right here? Sine of negative theta over cosine of negative theta. And I just figured out that already, didn't I? Negative sine of positive theta and cosine of positive theta, which just means, so tangent has kind of two different proofs. Go back to the original definitions or use what you just built just now in order to help you prove it. Okay, how does this help us? Strategy of so what? Yay, we know how to do negatives and positives, great. So finish up with that. And you know what? I think we're on example 1. Example 1, just use, I think it says that, yeah, use the property of even or odd to find the following. So use the property of even or odd to find the property, and we'll do this real quickly here. Let's do the one that we already know here. So sine of negative 30 degrees. All right, how does this really work here? Because in the back of the book, notice on the unit circle, you guys don't have any negative angles. Is that true? On this little unit circle right over here? Aren't there just positive angles here? So if I can somehow convert everything to positive angles, I can get back to this little unit circle that I can use. The only thing is I have some rules. And so, true. Once I get to that, I can get back to this right here. And sine of 30 degrees is 0.5 or 1/2. And da 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 da, I have the answer. Are we good? Tangent. Tangent of negative 5 pi over 3. The odd property for tangent tells me this right over here already. Is that right? I got to stick a little negative in front of it in order to get my value. And 5 pi over 3. That's like 300 degrees or something like that. Is that right? That's a y value is a negative root 3 over 2. The x value is a negative 1, positive 1/2. I chop down the 2's real quickly here. I have a negative in front. Oh, that's so fun. Look at that. There's a negative there. So it's actually a positive root 3. So we've got some time, just a little time. Just want to show you visually what this means here, real quick here, because this kind of gets a little bit off here. So what we originally thought, we want to find sine of negative 30 degrees. We don't find sine right down here. So what we can do is we just stick a little negative in front of our answer, and we just find sine of that one right there. We're good? So we get to move into the positive angle territory. So for tangent, instead of going all the way around like this is the negative 5 pi over 3, what we do is we say, you know what, we're going to stick a little negative in front of there, but we can use the unit circle because we're just going to look up 5 pi over 3 on our unit circle and find out what those coordinates are and then negate them. Are we good? I feel like I'm not connecting. Are we connecting or no?
Wait, so you're taking the 5 pi over 3, which is negative, and turning it positive?
By the even and odd properties, which allows me to use the unit circle. Because if I can get things back to a positive angle, I can use the unit circle.
So you're basically just like storing the negative away for a little bit until you can use it.
But depending which trig function, right? Because some of them are even, some of them are odd, so we just use that sort of property. Cool. Okay, and then the stretch. You guys ready for the stretch? Secant. Secant of negative 240 degrees. So now, oh man, Mr. Najeeb didn't tell us whether secant is even or odd. Bummer. Secant. So let's see, secant is the reciprocal of which function? Again? Cosine, I believe, right? Is it cosine? And for something to be reciprocal, instead of it being x, it's just going to be 1 over x, right? So then back to this little chart here. Does the x change or not change? Okay, so hold on. So we have this little concept. So this guy is going to be an even function, just like its reciprocal. So if that's the case, I need to figure out what secant of 240 is. I get back to my unit circle. I look up 240. I look at the x coordinate because I'm looking for cosine. And I just take the reciprocal of cosine. Are we good? And voila. Dun, 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 dun. Are we good with negative 2? I think so. Good. All right, I think we're done. There it is. So I guess we should just put this together here. So even, if you want the little list here, odd functions here. So the even functions are only cosine and secant. Those are the only even functions. It's always a trig function and it's reciprocal here. The odd ones are sine cosecant and tangent cotangent. Right, those are odd functions here. So we have our full list at this point. And we're really are done. How fun is that? We explored a little bit more into this graph world. And even though it's okay. With that, I'm gonna stop the recording and I'm gonna let you guys go.
Thank you.
And you guys enjoy the rest of your day.